Hello, my name is Anders, and today I will be presenting our paper, The Evolution of Auto-Distribution Robustness Throughout Fine-Tuning. This is work done in collaboration with Yaseman, Benham, and Becca. ImageNet v2 is the auto-distribution benchmark that was created by following the sampling procedures of the original ImageNet dataset as closely as possible. Here we show a collection of models evaluated on the ImageNet testset and a new ImageNet v2 testset. We call this collection of models our testbed models. In addition to the drop in accuracy between the in and auto distribution testsets, there is a clear linear relationship between the accuracies. To date, only a handful of models are known to significantly break away from this linear trend, but there are no known ways to systematically produce such models. The linear relationship tells that the auto distribution accuracy is entirely predictable from the value of the in distribution accuracy, and it's not sensitive to the model architecture, optimization, or robustness interventions, and we will not be able to close the performance gap in this way. Measuring the amount a model is above the line allows us to be precise about what kind of progress a robustness intervention gives us in a manner that controls for the in distribution accuracy. We define this distance above the linear fit as the effective robustness. Our goal is to understand why some models are above the line so that we can replicate this behavior for state-of-the-art models and decrease the performance gap between in and out of distribution data. Next, we show the main results from our work. We measure the evolution of the effective robustness of two models during training. First, we take a randomly initialized model and train it on ImageNet. It follows the linear fit set by the testbed models. Second, we use the same architecture, but initialize with weights from pre-training on JFT. The pre-trained model exhibits high effective robustness in the middle of fine-tuning, but vanishes as the model converges. We compare this result to the effective robustness from zero-shot clip models, and also our own zero-shot model constructed from a standard image classification model pre-trained on JFT. Our zero-shot model is constructed by evaluating it on ImageNet using a known map from the JFT to ImageNet classes. We find that our pre-trained zero-shot model matches the effective robustness of the best zero-shot clip models, but at 5% lower in distribution accuracy. This suggests that the zero-shot component of clip plays a significant role in the high value of effective robustness that the clip model achieves. Next, we investigate how details such as model size and pre-training data affect the effective robustness. First, we find that varying the size of the pre-training dataset increases the maximum effective robustness that's measured during fine-tuning. On the left, we show the results after training a series of models that was pre-trained on different sized fractions of the JFT dataset. Second, we find that the maximum effective robustness increases with larger model sizes. This is illustrated on the right, where we show the effective robustness for 3 different model sizes across models pre-trained on 4 different datasets. As already mentioned, the effective robustness vanishes at convergence. In our work, we explore several potential solutions to mitigate this problem, but we find that none of them are able to maintain both high effective robustness and high in-distribution accuracy. On the right, we show the results from varying the difficulty of the fine-tuning examples, where we measure difficulty by the Z-score. We select 5,000 hard, easy, and random samples from the CFAR10 training set, and we achieve higher effective robustness when training on harder examples. However, these models do not achieve state-of-the-art accuracy on the original CFAR10 test set. Finally, we analyze properties of the model early stop at maximum effective robustness. We observe that models with high effective robustness make very different predictions from the other models in the testbed. For example, among the 4.8% of examples that no model in the testbed gets correct, our best model correctly classifies 10% of those. For more details and additional experiments, please see our paper in the archive or send us a message. Thank you.